Section 36.2, the pre-equilibrium approximation. Let's look at this very general chemical equation. I'm not giving you real chemicals. We have A and B as the reactants. They form an intermediate I first, and then I is converted to P. We need to pay attention to this double-headed arrow. And this tells us we have a reversible reaction here. So you can go from A plus B to I. You can go from I to A plus B in this case. The forward reaction rate constant from A plus B to I is K sub F. The reverse reaction rate constant from I to A plus B is K sub R. From I to P, we also have a reaction rate constant. It's K sub P. And let's assume the reaction rate from P back to I is negligible. So we're not writing anything here. So now let's define this pre-equilibrium approximation. The definition of this pre-equilibrium approximation is this. We assume this A plus B and I are always at equilibrium. Alright, are always at equilibrium. So why is this called pre-equilibrium? Well, this is because, this is the first step, this is the second step. In the second step, the products are produced. So this is before the production of P. That's why it's called a pre-equilibrium approximation. And because we assume A plus B and I are always at equilibrium, that means the forward rate is equal to the reverse rate. The forward rate is K sub F times A times B, assuming the forward reaction is an elementary step. So over here, this is second order. One order with respect to A, one order with respect to B. And then there's a reverse reaction from I to A plus B. If you're looking at the reverse reaction step, again assume this is an elementary step, and then it's got to be a first order reaction. It's the reaction rate is K sub R times I. So it's right here. Well, at equilibrium, the forward rate is equal to the reverse rate. And therefore, we get the expression for the concentration of intermediate I. It's this. Alright, and then we know how fast this P is produced. The reaction rate is dP over dt. It's just Kp times I, assuming this is, again, an elementary reaction. So it's going to be Kp times I over here. And we know how to express I. I is this Kf over Kr times A times B. So over here. And then we define this part to be K effective, again for simplicity. The reaction rate is K effective times A times B. So it's going to be a second order reaction. Alright. With this K effective reaction rate constant. And this K effective is Kp times Kf over Ki. So when can we use this pre-equilibrium approximation? I think it's very helpful for us to simplify the differential equations. Again, we have 4 different species in this mechanism. We have A, B, I, and P. That means we can write out 4 differential equations, and it's pretty difficult to solve these 4 differential equations exactly. So that's why we resort to the pre-equilibrium approximation to simplify the process. So over here, but when can we use this pre-equilibrium approximation? This approximation is fairly accurate if this K sub P is much smaller than Kf and Kr. So what does that mean? So this step has to be much slower than this forward and this reverse reaction. So that means although I is converted to P, the conversion from I to P is so slow. Any changes made to I due to this step, is quickly replenished by this forward reaction, and the forward reaction from A plus B to I and the reverse reaction from I to A plus B are so fast that we can always maintain a fast equilibrium between A plus B and I, regardless the existence of the second step. Again, this step, this from I to P, is really, really slow. Now let me give you one example, a real chemical example. Let's say 2NO plus 1O2. We get 2NO2. This is a complex mechanism. It contains 2 elementary steps, actually 3. If you count this forward and reverse as 2 different elementary steps. Alright, so maybe I should change it to 3. So you go from this 2NO to N2O2, and you can go backward, and this N2O2 can react with oxygen to form 2NO2. So again, we have 1, 2, 3. 3 elementary steps. The reaction rate constant is Kf, going from 2NO to N2O2, and it's K sub R going backward. Now let's assume the so-called pre-equilibrium approximation. Again, we're assuming this forward and reverse steps are much faster than the third step. And then we have this equation here. This is assuming this NO and N2O2 are always at equilibrium. All right? And then finally, we can write out the reaction rate. It's going to be just dNO2 over dt. This is how fast the product NO2 is produced. But because of the coefficient 2 right here, we need to take that into account. All right, so we need to divide the production rate of NO2 by 2 to get the reaction rate. Okay, so again, the reaction rate is always the production rate divided by the coefficient, or negative consumption rate also divided by the coefficient in front of the reactant that's being consumed. So again, let's get back to this. We can write out this differential equation here. So it's going to be Kp times N2O2 times O2, assuming this is an elementary reaction. And then this is second order, so it's going to be Kp, assuming this is Kp, times this reactant to the power 1 times this reactant to the power 1. So right here. And then this N2O2 is an intermediate. We can use this expression here to convert N2O2 to the reactant NO, and then we get this expression. Now finally, this Kp times Kf over Kr is a constant. We define this to be K effective just for simplicity, and then in the end we know this reaction is going to be a third order reaction. This R is proportional to NO squared, and it's proportional to O2.